Good afternoon, everyone. So let's work on the assignment. So this is the example that we were talking about. So the number of hours on the average a college student in the US studies is 17. So that means mu is 17 hours. Okay. And sigma, the standard deviation, is 3 hours. And it also says that the hour distribution, study hour distribution, is bell-shaped or normal, okay? Normal distribution slash Gaussian distribution. Now, based on this information, answer the following question. Number one, find the probability that a randomly selected, meaning your sample size is 1. Let me write it in red so that you remember. Sample size is 1. A randomly selected student spends more than 18 hours a week. So find the probability that a randomly selected student spends more than 18 hours a week. So let's go ahead. And this is mu is equal to 17 and sigma is equal to 3. And we will need this, so I'm just drawing it here. Mu is equal to 0 and sigma is equal to 1. Mu is equal to 0 and sigma is equal to 1. Now, remember here, sample size is 1. That means we are dealing with the population distribution, right? So this is the population distribution. And this is the standard normal distribution. I drew it because I'll need it. So the probability that a randomly selected student spends more than 18 hours. So let's say this is where my 18 is. This is my X, okay? More than 18 hours is this probability. All right, this area. So we need to translate this X into the corresponding Z here. So this is gonna be right here, the Z value. And how do we find the Z? Using the formula Z is equal to X minus mu over sigma. So my Z is gonna be, in this particular case, X is the point in question, which is this 18 minus mu is 17 right here. All of it divided by sigma, which is, sigma is 3, which is 1/3, right? That's approximately 0.33. So this is 0.33, this point. So we are looking at this area. So probability that X is greater than 18 is the same as the probability that Z is greater than 0.33. And 0.33 gives you, if you look it up in the table, so probability of Z is greater than 0.33. Now, this is the area to the right. That means this area we are looking for. But if you look it up in the table for standard normal distribution, you get the area to the left, right? Area to the left of this point, 0.33. So how do I go and get the area to the right? Just you subtract it from 1. That's going to give you the complement. So 1 minus probability of Z is less than 0.33. And that is going to give me 1 minus point. So for Z 0.33, it gives me 0.6293. 6293. So 1 minus 0.6293 is 1 minus 0.6293 is 0.3707 is 0.3707. which, by the way, is nothing but 37.07%. 37.07%. All right. So that's the probability that a randomly selected student spends more than 18 hours studying per week. Now, the next question is find the probability that a randomly selected, still we are at this situation, n is equal to 1, a randomly selected student spends less than 15 hours studying. Then again, your 17 mu is right here, 15 is going to be somewhere here, right? So less than 15 meaning we are looking at this area to the left. So corresponding to this, there will be a z value here, right? This is your x, the other x, and we're going to find the z. So z is equal to x minus mu over sigma. X is 15 minus mu is 17, right? Divided by sigma is 3. That is negative 2/3, right? Which is, by the way, approximately negative 0.67. So that is the same as saying, so this is 0.67 negative. This is equal to probability of z is less than negative 0.67. So now we just can find it easily because we look in the table, z is equal to negative 0.67, negative 0.67, and that value is negative 0.2514, okay? 0.2514, that is 25.14%. So there is about 25% chance that a randomly selected student will spend less than 15 hours per week studying. Now the third question is this: find the probability. So third question, find the probability that a randomly selected student spends between 15 hours and 18 hours studying. So in that case, we are, by the way, looking for this area, the middle region. Remember, for the continuous case, probability is defined by the area under the density curve, okay? Area under the function. So this is the corresponding area in the scenario. All right. Now, there is going to be equal to probability of x is less than 18 minus the probability of x is less than 15. But both of these numbers we found, probability of x is less than 18 is given by this number, which is 0.6293. 0.6293 minus the probability of x less than 15, which is 0.2514, as 0.2514. So 0.6293 minus 0.2514, 0.3779, 0.3779, which is the same as 37.79%. So there is a 37.79% chance that a randomly selected student spends between 15 and 18 hours studying. Now, let's go ahead and change the game. In the next problem, okay, In the next problem, so let's go ahead and draw a line here. All right. In the next problem, I tell you that consider a sample of size 16 and answer the same questions. Okay, so this time your sample size is 16 as opposed to sample size being 1. In the last problem, you were dealing with population distribution. Here, you are dealing with sampling distribution, remember. Sampling distribution. N is 16. So let's answer the first question, then we'll go ahead and answer the second, third. So number 4, find the probability that X is greater than 18. Now, again, as usual, I said before, I made a mistake here on purpose. What is the mistake? Does anybody see what the mistake is? You have done the problem. Probability of X is greater than 18.
It's supposed to be X bar.
It's supposed to be what?
The probability of X bar.
Okay, great, thank you. Yes, it is supposed to be X bar. Can you tell me why?
Because there's more than one person.
Because there are more than one person, okay? So X bar is greater than 18. Now, when I am graphing this, or sketching this rather, this time, unlike here, this is the population distribution. So look, this is the population distribution. However, this is the sampling distribution, remember. So there is a difference. For population distribution, you have mean. For sampling distribution, you have mean as well, but it's denoted by mu sub X bar. For sampling distribution, you have standard deviation as well, is denoted by sigma sub X bar. Now, we need to find the mean and the standard deviation for these two. So who wants to help me out? Okay. Anybody wants to help me out here?
Is this the part where you convert you go into ZX bar, and then we'll solve it and convert to X bar minus mu over sigma minus n squared?
You mean square root of n?
Yes, that square root.
Yeah, that's further down, but I just want to get the answer to this. Okay. How do I find the X bar and mu sub X bar? I mean, mu sub X bar and sigma sub X bar.
Why don't we just look at the first graph?
Yeah, wouldn't it be 17?
Why?
Because it's a bell shape.
What is bell shape?
The graph. So it's like the same as the other.
Which graph are you talking about?
Like the one on the top. Oh, he's like at first.
You mean this one?
Yes.
Okay. So what's up with that one? How does that relate to this one, the bottom one, bottom left one? First off, remember, this is the sampling distribution. This one is the sampling distribution, right? So you are taking a sample of size 16. You can take many, many samples of size 16 from the original population, which is this one, right? Now, the distribution of all of this is bell-shaped, which is the bottom one. But why is it bell-shaped? Does it have to be bell-shaped, or is it possible that it is not bell-shaped? I am claiming that this is bell-shaped, which is correct, but why? And but why even we need it to be bell-shaped? Of course, we need it to be bell-shaped, but first of all, why is it bell-shaped? What argument can you present that'll tell you that it's bell-shaped?
Wasn't it that it had to be like the sample had to be less than 30?
No, it's just the opposite. Sample size has to be bigger than or equal to 30. That's when this bottom one will be always bell-shaped. But my sample size is actually less than 30. So this should not be a bell-shape. Or at least we can't assume it to be bell-shaped. However, I'm saying that, oh, it is bell-shaped, but why? Anybody? You guys did the problems, right? Alondra? Alondra? Danny?
Hmm. Uh, don't have an answer for you.
Monica?
I know it has to be 17, but I don't know why.
17? Where does 17 come from? It doesn't have to be 17.
Well, isn't it because it's like a mirror or something? Like, I don't know how to describe it.
Okay. Anyone else wants to describe it? Jessica?
It's bell-shaped because our original one, where it was just n equal, where our n was 1, where we're just talking about one person, they told us that it was normally distributed, and so it's bell-shaped. So if the first one was bell-shaped, then we know that this one is bell-shaped because we know that distribution.
Perfect. Does anybody see what she's saying? What Jessica is saying? Or everybody see what she's saying?
Yes.
Say, in the original problem, I said that the population distribution is bell-shaped, right? Or normal distribution or Gaussian distribution. So that means this population is normally distributed. If that is the case, even if your sample size is less than 30, it doesn't matter. Your sampling distribution will always be normal or bell-shaped. That's the reason. On the other hand, had I not given you this information, let's say I told you nothing about the distribution of the original population, in that case, you'd have to say, sorry, our sample size is less than 30, so we cannot apply the conclusions of central limit theorem. Sample size is less than 30, so we cannot apply the conclusions of the central limit theorem. Therefore, it's out. Okay, we cannot solve the problem. So in the exam, be careful. Make sure you understand. Don't blindly do it. Because there will be a situation where you won't have to do anything. And if you keep trying doing something, you'll go nowhere. So this one, even though the sample size is less than 30, which is 16, the sampling distribution here is still bell-shaped. or normal or Gaussian because the original population is normally distributed. And that means we can use the conclusions of central limit theorem, which says mu sub x bar is equal to mu, but mu we know is 17. So this is gonna be 17, this middle point, right? And sigma sub x bar is gonna be sigma over square root of the sample size, which is 3 over square root of 16, which is 3 over 4, that is 0.75. Okay, so sigma sub x bar is 0.75. Now you can go ahead and do the rest of the problem very easily. So z sub x bar, so 18 is gonna be somewhere here, right? Let's say this is my 18, that's x bar, it's not x anymore. Here it was x. Now here is gonna be x bar because we are considering average of 16 people. Now that's gonna map to some number here. So we are gonna find that number. So z sub x bar is equal to x bar minus mu sub x bar over sigma sub x bar. So z sub x bar is equal to x bar is 18 minus mu sub x bar is 17 and sigma sub x bar is 0.75, which is 1 over 0.75, which by the way is gonna be z sub x bar is equal to 1 over 7.75 is 3/4, which is becomes 4/3, which is approximately 1.33. So probability of x bar greater than 18 is the same as probability of z sub x bar being greater than 1.33. So this is 1.33. So we are looking for this area, which is equivalent to this area. That is 1 minus the probability of z sub x bar less than 1.33, which is 1 minus 1.33. If you look it up in the standard normal distribution table, 1.33 would give you 0.9082. 1.33, let me just double check. 0.9082, 0.9082. So 1 minus 0.9082 is 0.0918. 0.0918, that is 9.18%. Okay, so there is 9.18% chance that somebody average of 16 people would be greater than 18 hours. Now, next, let me do the same thing. Number 5, find the probability that average of 16 people is less than 15 hours. That means on the average, they would study or spend 15 hours or less studying. So 15 would be somewhere here, right? So 15. So we are looking for this area to the left, right? By the way, guys, are you guys okay? Me putting too many things on the same screen? Can you follow it or is too much?
Yeah, that's fine.
Yeah, that's fine.
Yeah, because I just want to keep these diagrams together so that I can compare them. That's why. That's the only reason. Okay, now less than 15 x bar probability. So we are going to have a corresponding. So this is, remember, not x. This is x bar. Like here, this is x. Here it's x bar because we are dealing with average here because of the sample size being bigger than 1. So this would map to some value here, right? There will be my z. So how do we find that z? Z sub x bar is equal to x bar minus mu. So 15 minus 17 divided by 0.75, which is -2 over 0.75, which comes out to z sub x bar is equal to 2 divided by 0.75, which is 2.67 negative 2.67 roughly. I'm rounding it. So this is going to be negative 2.67. So I'm looking at this area. So there's going to be probability of z sub x bar being less than negative 2.67. And you can look it up in the table. It'll give you this number, negative 2.67. Negative 2.67 is gonna give me 0.0038. 0.0038, which is, by the way, 0.38%. All right. The next thing is this. Find the probability that, so this is number 6. Find the probability that average of 16 people falls between 15 and 18 hours. 15 and 18, which is, by the way, we did it before. That's the same as probability of x bar less than 18 minus the probability of x bar less than 15. Okay, probability of 15 less than x bar less than 18 is the same as probability of x bar less than 18 minus the probability of x bar less than 15. Okay, probability of x bar less than 18, we already have that number, which is 0.9082, because probability of x bar, this is, oh, I have to rewrite it. I have to convert this thing, one more line, I don't have enough space. Probability, this is the same as probability of z sub x bar is less than 1.33, because 18 converts to 1.33 minus probability of z sub x bar less than negative 2.67, which we just found right here. And if I plug in the numbers, so this will give me 0.9082, 0.9082, this first one, and this minus the second one is 0.0038, this one, which is this number, 0.0038. If you do the math, 0.9082 minus 0.0038 is 0.9044. 0.9044, which is 90.44% chance, which is, this is 90.44%. So this is the area I'm talking about, which is the same as this middle portion. And that is how you will do these problems, okay? Both of these. Okay, in one case, we are dealing with population. In this case, we are dealing with population. And in this case, we are dealing with sampling distribution. Sampling distribution. In one case, I'm dealing with population. In another case, I'm dealing with sampling distribution. Remember, which one you are dealing with, you need to be clear on that. Then you'd be able to apply the appropriate distribution and formulas. Now, the last problem I gave you is the same thing, it's just n is equal to 49. here I gave you n is equal to 16. Just do the same thing for n is equal to 49. In this case, it doesn't matter what the distribution of the original population is. In this case, distribution of the original population is irrelevant because this is greater than or equal to 30, right? If it is greater than or equal to 30, it does not matter what the distribution of the original population is. Sampling distribution is always going to be bell-shaped. Any question, anybody, about this?
Yeah, I just have a question about one of the first problem, because I think the only thing I screwed up about that answer was that I didn't do 1 minus 60.6293. So when do you have to do 1 minus the given problem, the like 6.6293, whenever you're doing like
No, it depends where
Depends.
where you are. Yeah, it
Mhm.
depends. If you're looking for the area to the right, then you have to subtract from 1. Look, I'm saying here z greater than 0.33, right?
So
So
it's
that means-
you're looking for, so it's whenever you're looking for the highest number, whenever it's the highest number, it's always going to be on the right.
No, not the highest number so much. Whether the problem is asking greater than or less than. See, this problem was asking the probability of x
Okay, I
being
see.
greater than.
So then you're supposed, so if it's greater than, then you have to do 1 minus
Yes,
that, and then if it's less than, you don't have to worry about that.
correct.
Okay, all right. Thank you.
Mhm. Anybody else has any other questions? All right. Let's clean up the screen. Next, I want to do this problem. People are having difficulties with this problem, so I'm gonna go ahead and work on it. This problem, I made it up, but yet I don't like the wording of it. The reason is that, okay, first of all, is the problem easy to understand by reading it? Don, what do you think?
No, there's too much going on.
Too much going on, okay. Anybody else has too much going on? I believe there should be other people with similar feelings.
That was my problem too.
That was your problem too, okay, good. Let me explain it to you in layman's terms, how an ordinary person would explain it. So let's say cigarette company, okay, cigarette company C, okay, some cigarette company C. They're saying that we have reduced the amount of nicotine in our cigarettes. Because nicotine is bad, you want to consume less of it. We reduce the amount of nicotine in our cigarette. They're claiming that. But you want to figure it out. Hey, did they actually reduce it? So what you do, you go out and randomly select 50 cigarettes. And then for each of them, you find the amount of nicotine, and then you find the average of these 50. So you find the X bar, okay? Now this X bar happens to be 11.8 milligrams, or yeah, milligrams. Now, based on this analysis, would you say that the cigarette manufacturer C is telling the truth? That means their claim is valid. You would accept it. So that's what the question is. Now, the way you do it is this. There are a few things here. It's a straightforward application of central limit theorem. You don't know what the original distribution of the population is. Originally, they tell you that the mean amount of nicotine in the cigarette is 12 milligrams with a standard deviation of 1.5 milligrams. All right. Now, you don't know about the distribution. It could be bell-shaped or it could not be, but your sample size n is greater than or equal to 30. So you know for sure your sampling distribution is gonna be, bell-shaped, right? So if the sampling distribution is bell-shaped, then you could figure out what are the chances that if they haven't done anything but claim that we reduce the amount of nicotine in the cigarette, what are the chances that even if they didn't do anything, the average of 50 randomly selected cigarettes would be less than or equal to 11.8. If that chance or that probability is below some threshold, then you would say, oh, okay, maybe they did make some changes. But if it is not below that threshold, then you would say, oh, maybe chances are not as much that they actually made some changes. Okay, that's what the problem is. So again, in layman's term, it is basically somebody is claiming that they did something, which is the cigarette manufacturer reducing the nicotine, and you want to test it. You want to find out, did they really do it? Then you'd say, okay, if you didn't know statistics, what would you do? You'd say, on the average, you know, there is 12 milligram of nicotine in a cigarette, and then you go out and survey, and you find that 11.8 milligrams. Based on this, does your common sense tell you they reduced it enough? That's what basically it boils down to. Is the framing of the problem clear now? Does it make a little bit more sense, Don?
Yeah, it makes a little bit more sense. It was funny when I came across this problem, I was kind of like, what the hell? My spouse looked at it. My spouse likes this problem. He's crazy, but he likes this problem. He was like, oh, this is a good problem. And then he's like, have you figured it out? I was like, no. And then he just walks away from me. But I used the example on that you provided on the homework, and I was able to figure it out.
Okay. All right. Cool. Anybody else? Any other thoughts, comments on the problem? I admit that this is not the best worded problem. Okay. So I'll give somebody extra credit points if you can state this problem in a better way and in a more concise way. Okay. I don't know if it has something to do with language barrier or English not being my first language or anything like that, but I couldn't find any other easier way of explaining it.
I think, Mr. Hussein, it's because you speak very, very formally for the most part, and it comes out that way, and not a lot of people do. So you write like that as well.
Yeah, you're not the first person that told me. At least a couple of other people told me this is something I can't get rid of. The way I talk, this is exactly how I write as well. So, but in the US, people talk in one fashion or one style rather, but when they write differently. So that's probably what it is. So Don, what is the solution? What is your suggestion here?
So I took X bar and I subtracted the.
Oh no, not that solution. I'm asking.
Oh, that's you wanted the solution to the problem.
So okay, this is a job for you. You and your spouse sit down and reword this problem so that everyday Tom, Dick, and Harry can understand this problem. Okay.
All right, I'm gonna ask him and see what he says.
Okay, so you guys sit down tonight or sometimes just figure it out an easier way of explaining this problem to somebody who doesn't have stats background, and they would still at least understand the problem. That way it's easier. So go ahead and do that and let me know, please. And anybody can do it. I'll give you extra credit. Okay, please be my guest.
Thank you.
Mm-hmm.
What I was
All
gonna
right,
tell
so-
you, don't
Yeah.
be upset that you speak formally and write formally. That's not a bad quality. So that's a good quality.
Okay, thanks. So now let's go ahead and do this problem. So I'm gonna take the background off. You guys know. So my sample size, let me write it in red so that you remember, n is equal to 50, okay? Sample size, which is greater than or equal to 30. That means sampling distribution would be what? Normal or Gaussian. Now let's go ahead and draw this diagram. In essence, this is the sampling distribution, mu sub x bar, sigma sub x bar. Now remember, sigma sub mu sub x bar is equal to mu according to the central limit theorem. But in our case, mu is given to be 12 milligrams. And sigma sub x bar is equal to sigma over square root of the sample size, which is square root of n. Sigma is 1.5. You divide it by sample size is 50, so square root of 50. And if you do the math, it comes out to be roughly 0.21. So sigma sub x bar is 0.21. Now, the problem basically boils down to finding out, oh, okay, you went out and you found the average for 50 people to be 11.8, not people, 50 cigarettes to be 11.8 milligrams, all right? 11.8 milligrams. And then if they didn't do anything, what are the chances that you will find 11.8 or less for average? So mu is, by the way, mu sub x bar is 12. So 11.8 is somewhere here, 11.8. So what are the chances that even if the manufacturer didn't do anything, you will still get less than or equal to 11.8 milligrams, okay? If that chance is higher, that means more likely that the manufacturer is not telling the truth. If that chance is lower, that means, oh, by random luck, it couldn't have happened easily. There is more chance that they actually did something. So let me go ahead and do the problem, and then I will explain it to you again. So mu sub x bar is equal to 0, and sigma sub x bar is equal to 1. So now this point, this is my x bar, the average, would map to some number here, which is going to be z sub x bar. So it's going to map right here. Now, how do I find that? Z sub x bar is equal to x bar minus mu sub x bar over sigma sub x bar. So x bar is the point in question, which is 11.8. So 11.8 minus mu sub x bar is 12 by the central limit theorem's conclusion, and sigma sub x bar is 0.21. 0.21. If I do the math, I get 11.8 minus 12 divided by 0.21. That gives me 0.95, approximately negative. So z sub x bar is equal to approximately equal to negative 0.95. So this is negative 0.95, negative 0.95. So in essence, we are looking for this area. So probability that x bar is less than 11.8 is equal to probability of z sub x bar is less than negative 0.95. Now, if you look it up now, who is it? Let me find the person. Jacob. Jacob, are you there?
Yes, I am.
So now you tell me,
Mhm.
this one, do we need to subtract it from 1 or no?
11.8, correct? I don't think so, because it's the X bar is on the less than. I don't, it's on the less than, right? because it's the X bar is less than, or is it the other way around? Is it like because it's greater than the 11.8 is greater than, so we gotta. I think we're supposed to not subtract, right?
Yes, you are not supposed to
Okay.
subtract, because
Okay.
less than means you just look it up in the
Okay.
table. If it is greater than, you're looking for the complement, and that's why you need to subtract. Okay, so z sub x
Woo!
bar, okay, z sub x bar is less than negative 0.95, and for negative 0.95, what do we get? Less than negative 0.95. 0.1711, 0.1711, that is 17.11%. So there is a 17.11% chance, or say roughly about 17% chance that, okay, if the manufacturer did not do a single thing and they just completely made up this statement and said that they completely lied, let's say. I hate to use the word lie. They completely misrepresented themselves and said, hey, we reduced the amount of nicotine, okay? Even after that, you have about 17% chance that you will come up with 11.8 or less, okay? Even if they did not do a single thing to reduce the amount of nicotine in cigarette, there is a 17% chance that you will get an average of 11.8 or less that you got, okay? Which means 100% minus 17%, which is, by the way, 83%. There is an 83% chance, you could think of it that way, that they actually did something, probably. That's why you're seeing this. So 17% chance that they haven't done anything, okay? And you got that lower number. And there is an 83% chance the other way around, which is probably they did something, and because of that, you got that number. So that's kind of how you should be thinking about it, this problem. Normally, the rule of thumb that people use is 5% or 0.05, okay? If this probability is less than 0.5%, I mean less than 5% or 0.05, in that case, you say, oh, okay, maybe chances are very high, or 95% chance that they did something. Because of that, the amount has come down. And there is a 5% chance that they didn't do anything, and the amount still came out to be lower. Hopefully this makes a little bit more sense, right? Any question, anybody? No questions? Everybody okay?
How come we have to do the 100% minus 17 again? Is it because we're trying to find it on the other
So
side?
if they didn't do anything, there is still a 17% chance that you will get the amount that you got, okay, this or less.
Yeah.
So even if they didn't do anything, so intuitively you could think of 17% chance that they didn't do anything, you still got it less than the average, right? Then complement of, 17% is 83%, right? 83% chance that they probably did something.
Oh, I see. I see. So it's just the opposite of it.
Yeah.
Okay.
Complement, yeah. Anybody else has any questions? All right, that kind of takes care of everything about sampling distribution, central limit theorem, and etc. Okay. So we are gonna talk about point estimates. What is a point estimate? Point estimate is something that you get from a sample, to put it simply. Okay? Point estimate is something that you get from a sample. I write it kind of in a formal way. A point estimate is a single value derived from sample to estimate the population parameter. Simply speaking, this is what it is. X bar is the sample mean. You use this to estimate the population mean mu. So X bar is a point estimate. X bar, you don't get it from the entire population, right? You get it from a random sample that you take. Similarly, P hat is the point estimate for proportion, okay? And you use it to estimate the population proportion. Similarly, S square is the sample variance. You use that to estimate the population variance, sigma square. So these guys on the left are called point estimates, okay? They are statistics because multiple of them. Each of these is some characteristic of the sample. So these are point estimates. These are point estimates. Okay.
What did you say you used the X bar one for again?
Sample mean. Sample mean.
Thank you.
Mhm. Okay. All right. Next, we are going to talk about point estimator, okay? So let's go ahead and talk about that. Point estimator is the formula or function that you use to find the point estimate, okay? So again, point estimate is some characteristic or some attribute that you get from the sample. Remember, point estimate is some characteristic or some attribute that you get from the sample. Typically, you use it to estimate the corresponding population parameter. So for instance, once again, X bar is the sample average, right? X bar. X bar is the sample average, right? You use that to estimate the population average. P hat is the sample proportion. You use that to estimate the population proportion. S square is the sample variance. You use that to estimate the population variance. All right, so next, the formula, once again, that you use in order to estimate, in order to find the point estimate is called the point estimator. And I'll show you different formulas that we use. The next term is the parameter space. What is the parameter space? The parameter space is denoted by omega, the Greek letter omega. Now, it is representing the set of all the possible values that your population parameter can take. Remember, once again, I said it before, X bar is the sample mean, mu is the population mean. This is a statistic and this is a parameter, okay? P hat is the sample proportion, P is the population proportion. This is a statistic and this is a parameter. And S square is the sample variance, which is a statistic, and sigma square is a population variance, which is a parameter. Okay. Now, having said that, the possible values for any particular parameter is the parameter space. So easiest way to get a sense of it is this. Think of this. Think the number of hours a student studies at Hartnell College per day. Number of hours per day a student studies at Hartnell College. So that's the parameter you're looking for. That means the mu. As you know, the range for this mu is going to be as low as 0 or as high as 24, because there are 24 hours in a day. So your parameter space is going to be this interval, 0 to 24. Even if you wanted, you couldn't study more than 24 hours in a day. Even if you wanted, you couldn't study less than 0 hours a day. It has to be in between these. Okay, so this is the parameter space for the mean. Now, you could think of also proportion. Let's say, what percentage of the students at Hartnell go to the gym regularly 3 times a week or more? Okay, what percentage? So you could have as low as 0%, right? Or as high as 100%. It cannot be anything more than that or less than that. So 0% is 0 and 100% is 1. So it is between 0 and 100. I mean 0 and 1, not 100. So the space for the parameter is dependent upon the context, what you're talking about. Okay, what is the context that you're talking about? For parameter space for sigma square, okay, it cannot be less than 0, because sigma square is a square, right? It's always 0 or more, so it has to be greater than or equal to 0. You can think of variance or sigma square as having this property. Variance cannot be less than 0. It has to be 0 or more, or also known as non-negative. Non-negative means either 0 or positive. So that's that. Next one. Okay. So I told you, you have formulas for estimators. So X bar, this is the formula for X bar. That means you add up all the numbers. This is the summation notation. Summation I is equal to 1 to n x sub I, right? Summation I is equal to 1 to n x sub I, and you divide it by n, which is just a fancy way of saying add all the numbers and divide it by the total number of data points. That's what you do when you're finding average. Okay, then when you're talking about sample proportion p hat, you divide by the total number of people or total number of items that you surveyed, and out of that, how many of them fell under certain group. Okay, I think I made it harder than it should be. Let's say you asked 100 people, and out of 100 people, let's say 60 of them said they support abortion. Okay, so your p hat is going to be 60 out of 100, or 60%, right? Or 0.6. All right, so that's what the formula for point estimator. Now this is the formula that you have used. Okay, this is the formula that you have used for sample variance, which is s square is equal to 1 over n minus 1 times summation I is equal to 1 to n x sub I minus x bar whole square. So this is the formula for the estimator, s squared. All right. Next, we are going to talk about, let's see, what is the next in the slide actually. Oh, biased and unbiased estimators. Okay. So this is an important topic. If you have a statistic, let's call it theta head, okay? And this theta head could be one of these in our case. It could be X bar, it could be P hat, or it could be S squared. These are all different characteristics of sample. Generally, we use theta hat to represent one of these, okay? So if you have theta hat sample statistics, so expected value of theta hat, if that is equal to theta, which is the population parameter. So we could replace it by theta hat by X bar, okay? In that case, theta is gonna be mu. We could replace theta hat by P hat. In that case, we are gonna be using P for theta. We could use theta hat by S square. In that case, we are gonna have sigma square. Do you see? So general notation, in general, if you have expected value of theta hat is equal to theta, then it is called, theta hat is called an unbiased estimator of theta. Unbiased estimator of theta, okay? Now, let's go ahead and give you some examples of something that is not unbiased, okay? That is not unbiased, meaning that it is biased. So if, by the way, so let's define it first. If expected value of theta hat is not equal to theta, then theta hat is a, not an, a biased estimator. All right. If expected value of theta hat is equal to theta, theta hat is considered unbiased estimator, whereas if expected value of theta hat is not equal to theta, then it's called a biased estimator. There are three situations we're going to talk about here, which I kind of already talked about. We have the following scenario. Expected value of X bar, by the way, is actually mu. Expected value of P hat is actually P. And expected value of S square is actually sigma square. So these three are unbiased estimators. Unbiased estimator. Okay. On the other hand, expected value of S is not equal to sigma as one would expect. It is not. So therefore, this is a biased estimator. It is a biased estimator. All right. That's what it is. So now there are some typos here. Please fix them because I couldn't get them to work in the PowerPoint. So this should be E of S is not equal to sigma. It's not equal, and this is S square, not S times 2. And this is also sigma square. And this is P hat, which is P here. And this is X bar. So I have written them down here. Expected value of X bar is equal to mu. Expected value of P hat is equal to P. Expected value of S square is equal to sigma square. So there are some typos here. PowerPoint doesn't take LaTeX very friendly. Okay, so it just came out to be different. But I'm writing it down here so that you have it. Any question, anybody?
None, not yet.
Okay. Okay. let's go ahead and talk about the next topic. We're going to talk about confidence interval, okay? So before I do this, two remaining main topics for the semester are confidence interval and hypothesis testing. These are the two things. There are a lot of parts to juggle here. There are a lot of parts to play around with here. And what we are going to do, we are going to go ahead and structure them. So many years ago, I forgot the name of the student. She was taking this statistics class because she had Alzheimer's disease history in her family. If you do math, by the way, it helps you exercise your brain and it keeps your brain healthy. So she took this math class. And so when I came to confidence interval and hypothesis testing, there are too many things. It was a bit difficult to remember. So she came up with an acronym. And to this date, I use that acronym. And thanks to her, but unfortunately, I forgot her name. It's called PMS, okay? And it is not what you are thinking it is. What is PMS in our context? P stands for proportion. M stands for mean. And obviously S stands for standard deviation. That's the PMS structure. What is it? We are going to do confidence interval for proportion. We are going to do confidence interval for mean. We are going to do confidence interval for standard deviation. Similarly, we are going to do hypothesis testing for proportion, hypothesis testing for mean, and hypothesis testing for standard deviation. So these
Is
are
this where you say the biology comes in?
What is it?
Is this where you say the biology comes in?
No, this is
Because you're saying hypothesis testing, it just reminds me of biology.
Yeah, statistics and hypothesis testing is being used in many fields. There is no field on the face of the earth where you couldn't use statistics if you wanted. Okay. Literally, the statistics, its domain is the universe. Okay. So anyway, so remember this PMS structure: proportion, mean, and standard deviation. All right, so let's talk about this confidence interval. A confidence interval for a population parameter is an open interval of the form AB, okay, which we assign a certain confidence level that contain the population parameter. This looks too academic. Let's make it simple. Bring it down to ordinary people's language. So let's see. Okay. Let's say I ask one of you to go ahead and find the average number of hours Hartnell students work per week. So you go out and you ask randomly 100 people, okay? And you find the average of those 100 people and you come up with a number X bar. Let's call it 10 for simplicity. They they work 10 hours per week, okay? And obviously this is a sample. This is a statistic, meaning it's coming from a sample. You use sample statistic to approximate or estimate the population parameter mu. Now, this is not going to be the exact number. Extremely unlikely that this is going to be the exact number of hours that the college students at Hartnell work. It could be less or more. So now you can think of it as an ordinary person who doesn't know much of statistics. Oh, okay, yeah, I got 10 average number of hours by sampling 100 people by collecting data from 100 people. How good or bad could it be? So it could be like as low as maybe 10 minus 8, give or take 2 hours, right? So 10 minus 2 or maybe 10 plus 2. So you're saying that, okay, it could be as low as 8 or as high as 12, okay? What you just did, you just created a confidence interval without using any mathematical knowledge. And you know, people do it all the time. You don't think that people are sitting down with, you know, formulas and table and algorithms to figure out these confidence intervals. People are doing it all the time. So when you are, let's say you're driving from here to San Francisco, you're thinking, oh yeah, you know, it should take me an hour and a half to get to San Francisco. So give or take, you know, 15 minutes. So it could be as high as 1:45, an hour and 45 minutes, or as low as an hour and 15 minutes. You just created a confidence interval. That's exactly what it means to create a confidence interval, okay? You did it with your brain and your knowledge and your experience, but in the realm of statistics, we formalize it and we have a method for doing it. And it is all based off of central limit theorem. Remember, we talked about central limit theorem. Central limit theorem has a bell-shaped curve or sampling distribution curve for x bars, right? For all the x bars of certain sample size n, this is the bell-shaped curve. Now, all the samples of some sample size n, you have a distribution for p hats too. P hat is the sample proportion. This is the sample average. And this is the one that we will be using to find the confidence interval, okay? So like the way we had sampling distribution for sample means, we have the sampling distribution for sample proportions too. There is an equivalent version of central limit theorem for sampling distribution. And you will see there is something called NP greater than or equal to 10, and n times 1 minus p is also greater than or equal to 10. These two conditions have to be satisfied, okay? And most of the times our sample size is big enough so that we don't really have to worry about it. So the way we use the conclusions of central limit theorem for mean or average sample mean, exactly the same way we are going to be using the conclusions of central limit theorem, but this time for population proportion, not for population, I mean sample proportions, not for sample means, okay? And the mathematics and analysis behind that is a bit more involved and beyond the scope of this class. Even though I talk about it in the reading materials that I provided you, you are not required to understand it, but it would be nice if you did. But overall, I kind of expect you to get a sense of central limit theorem, how it works for the mean. It should work for proportion as well, similarly, okay? So that's at least what I want you to know. The way central limit theorem works for mean, it also works for proportion too. So to summarize here, confidence interval is the open interval that you create, okay? And associated with it, certain confidence level. Okay, so for example, you may say that we are 90% confident that the true population parameter, that means it could be population mean or population proportion, falls in the open interval this. Here, 90% confidence level. What does that mean? It means that if you were to create many confidence intervals like this by taking a certain sample size. So let's say you take sample size of 100, just one sample, you create a confidence interval. Let's call it A1, B1. You take another sample of size 100 and you create A2, B2. And how many can you make? As many as you want, right? Pretty much. So let's say if you made 1,000, so A1000, A1000, B1000. So you have taken samples of size 100, but 1000 of them. 90% confidence level means that out of this 1000, 90% of this, 90% of 1000 of them will actually include the actual population mean or proportion that you're looking for, or in general, the actual population proportion that you're looking for. So 90% of 1000 is 900. So 900 of them are going to actually include. So 900 of these intervals are going to include the population proportion or population mean or in general population parameter that you're looking for. And 10% may not, which is 100 of them. So approximately 900 of them will include the true population value, okay, population parameter, and about 10% or 100 of them will not include. That's what it means. Now, if I had 95% confidence level, that means that 95% of 1000, right? And there'll be approximately 950 of them would include the actual population parameter, and about roughly 50 of them will not include that population parameter. Okay, confidence coefficient versus confidence level. Confidence coefficient is the probability associated with this. So this interval, let's say I create a confidence interval. What is the probability that okay? What is the probability that it will include the population parameter? Now, if this probability is expressed in terms of percentage, okay? If it is expressed in terms of percentage, it's called confidence level. So confidence coefficient is the actual probability. If you convert it into percentage, it's called confidence level. And this is what you will be using more often. For whatever reason, you know, statistics is a subject, it's sometimes hard to learn and hard to teach both. Because people, some of these terms are kind of interchangeable or could be slightly meaning different things. And sometimes people get too picky about these things, you know, how you express these results, okay? But particularly if you are doing it for academic research purposes, you have to say things in a certain way. But in our case, we are not doing academic research, but we can be a little bit informal. They kind of are related. So confidence coefficient is probability, which is in decimal probability, right? And this is in percentage. So what was the big difference, big deal about it? So, you know, I could say confidence level versus confidence coefficient, kind of interchange these kind of things. So don't get too you know, strict about these things. So just remember, the formally it means that confidence coefficient is the actual probability, maybe in decimals, and confidence level is in percentage. Okay. And also sometimes people say I'm 90% confident, means there is 90% chance that the interval AB include that population parameter. Some statistics folks are going to get very upset with you for saying that. No, it's not 90% confidence. Okay, 90% probability. Okay, they would say 90% confidence level, which means if you were to create many of them, 90% of that approximately will include the population parameter, and 10% of them will not. And it will make a little bit more sense as I spend more and more time on this. So now, how do you find the confidence interval for population parameter? There is the formula. Now you'll see the normal distribution, standard normal distribution, and all of those things. Z sub alpha over 2, okay, times square root of p hat minus, p hat times 1 minus p hat, all of it divided by n. So this is something you could think of it as the standard deviation of the sampling distribution, okay, along that line. All right, there's the standard deviation of the sampling distribution, like sigma sub x bar. Any questions, anybody? No questions? I think I'm gonna stop here for the day. And also, by the way, make sure to go over these problems, and you will you will need to know these problems for the upcoming midterm. And please do not hesitate to bring in questions to the class after trying it at home. I have recorded all of these sessions and I have emailed them to you. You can just look at those recordings and you'll see that I talk about central limit theorem, normal distribution, standard normal distribution, sampling distribution, all of these many, many times. Okay, you can't go wrong if you watch the videos. All right. Okay, and that's all pretty much for the day. Thank you so very much. Okay, let's stop it here.